Alrighty, kids, welcome to the 4th edition of Atomic History Notes, or the history of the atom. We're going to start today by doing atomic structure bellwork number 3. So it has a chart up here, and it's also got a back to it. Okay, so I want you guys to go ahead and do this top chart and also answer these couple of questions and give me some good drawings about atom models that we've seen already. So hit pause right now and work on this bellwork, and then I'll go over a couple of select problems. So now that you've had some time to work on this, why don't I just do this row right here? So we have a phosphorus with a -3 charge. Okay, we're told its mass is 31, and that's all we got. Okay, well, let's see what we can do here. Remember, the most important piece of information about any given atom is absolutely, positively, its number of protons. Okay, that defines the atom. So it's Z, number of protons. Okay, so it's phosphorus. Well, all phosphorus atoms have 15 protons. So that's 15. Remember, number of protons and the Z are the exact same thing. Well, the mass is equal to protons plus neutrons. So we have a mass. This particular phosphorus has a mass of 31. All phosphorus have 15 protons. So 15 plus what equals 31? Well, that would be 16. How many electrons are we talking about here? Well, charge, in this case, is -3. I know that I have 15 protons. So 15 minus what equals -3? That would be 18. And if we're going to give the full atomic symbol, we're going to start with the P in the middle for phosphorus. The mass goes up here. That's going to be 31 in this case. The Z, 15. And the charge, -3. And you're like, wait, Mr. P, it had the 3 minus instead of -3 at the beginning. Does that really matter? No, it doesn't really matter. It's just a little formality thing. Don't worry about that. I'll never mark off something that you put -3 where you should have put 3 negative. So no worries there. Now down here, Bohr's model, let's remember we have a little positive nucleus at the center. It's tiny. And then we have these perfect rings that are forming around that. So I'll get some nice little circles. So get some perfect rings forming around that. Okay. Something like this. And you get another one of those rings, blah, blah, blah. Ooh, that's a very big one. So on and so forth. So it looks something like that. And then he had little electrons flying around in there. Boom. Do scientific models tend to become more simplified or complex over time? Well, definitely more complex because we learn more information, and so we can add on to our models. Remember that first model was just a ball. So this is Dalton's billiard ball model, or the marble. So it's just like a ball. And then we had J.J. Thomson's plum pudding. So it's sort of like a positive pudding with like negative little sprinkles in it. These are negative signs. So on and so forth. And we end with Bohr's model here. So let's go ahead and get to some new stuff. So, history of the atom, notes part 4. So we're going to sort of start with Bohr's model and extend it to quantum mechanics, which is a fancy sounding word. But let's not forget Bohr's model. We got the positive nucleus in the middle. We got electrons floating around in orbits around that. Low energy close to the nucleus, high energy far away from the nucleus. So, by the 1920s, we discovered that Bohr wasn't exactly correct. His model works great for atoms with small numbers of electrons. So again, hydrogen, lots of times just has the one electron. It works great for hydrogen, pretty good for helium, okay for elements after that. But when atoms had more electrons, it started to really fall apart on us. So Bohr's model didn't really hold up when we compare it to most elements. So we realized it needed to be modified, but no one really knew what to do. So we're like, okay, we know that this isn't the right answer, but we don't know what the right answer is in terms of our atom models. So let's look at a couple of fun pictures here. So what do you see in this picture? So maybe hit pause for a second, take a look at this picture and tell me what you see. So you hit pause for a second, and here's what you could see. You could see an old woman, okay? So here's the old woman's eye. Here's her big old schnoz right here. This is her big nose. And here's the woman's mouth. And here's her jawline. Okay, so you may have seen an old woman, but you may also see a young woman. So here's a young woman's necklace right here. This is her necklace. This is her jawline. Here's her tiny little nose, and here's her eye. And she's kind of looking this way, kind of over this way. And here's her ear right here. And this is her nice hair and that kind of thing. And so you're like, which one is this? Is it an old woman or a young woman? Yes, it's both. Or what are some other fun ones? What about this? So pause it for a second. Think about what you see, and then I'll tell you what I can see. So here, I'm looking at this. First thing I see is I see a bunny rabbit. So here's the bunny rabbit's ears right there. Here's its eye. Here's its little nose. Okay, you can kind of imagine little whiskers coming out here. Okay, and the bunny rabbit is looking this way. But what about a different perspective? Some of you may have said, I see a duck. So here's the duck's beak right here. It's kind of open beak. Here's the duck's eye, and the duck is looking this way. Okay, so again, which one is it? Is it a rabbit or a duck? Yes. Maybe we can try one more here. What about this one? So what do you see? So a lot of people say, I see a guy's face with like glasses and that kind of thing. But what if you change the perspective this way? I see the word liar in cursive. Liar! Mr. Pelcher's a liar. So some things can be two things at once. So when it comes to whether an electron is a particle or a wave, the answer is yes. It's both simultaneously. So an electron is and so you see how this word can be the word particle? Check it out. So you got P, A, R, T, I, C, L, E. Or you could also read the word wave. W, A, V, E. So electrons are both particles and waves at the exact same time. They're kind of confusing. So enter Louis Victor de Broglie, or maybe Louis Victor de Broglie. And, you know, de Broglie kind of looks like a piece of broccoli. You know, I always draw this. Hey, what's up? Here we go. Because his head's kind of shaped goofy like a piece of broccoli. Haha, Mr. Pilcher's got jokes. Anyways, so he was the first to kind of show that electrons have wave-like properties. And so his model was like this. Okay, we have the positive nucleus at the center, and then around that, instead of having these pretty little perfect circle orbits, we have like these they're sort of forming circles, but they're like waves. So like if you watch me draw this, I think that'll kind of help you see it a little bit better. So we got the positive nucleus, and the electrons around it are, instead of these perfect little circles like that, they're kind of like in waves, sort of like waves of negative energy around that nucleus. Yep, so we kind of have these waves, and they sort of form circles, but you can't really call these circles either. They're sort of like waves, and it's just sort of like negative energy. And so that's de Broglie's contribution. That was his model of the atom. It's a little bit different than Bohr's. And now we got Erwin Schrödinger. He's just a very serious-looking person. Anyways, so let's see his contribution. He developed a really complex math equation to describe electron motion. So if you don't want to be triggered right now, I suggest you put your pencil down and don't try and write all this down. But here are his notes from a Georgia Tech University lecture. So he's like, blah, 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 Schrödinger equation, Schrödinger equation, yep, yep. And you can't forget the time variable in the solution. Oh, yeah, yep, don't forget that operator, the Hamiltonian operator. And don't forget about the momentum operator, yep, la, 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 look at all this, dependent portion. Oh, yeah, here it is, looking great, makes sense. You guys are following along. Oh, don't forget about the boundary conditions. So what does this mean? Oh, it means this. It means the standing wave results from the requirement that there be blah, 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 blah. Here's what you can really say that his lecture meant. We have no idea where an electron really is. Okay, so the whole orbits idea where they're going around in perfect little circles and we know where it is at all times, not a thing. Okay, we don't really know where like an electron is or where it's going lots of times. We know a lot less about the electrons than we thought we did. And so that's Schrodinger's contributions. Like, so what did he contribute? He basically helped us see that we know less than we thought about where an electron is. So he kind of helped us realize that we're going backwards a little bit. And finally, Werner Heisenberg. If you ever watch Breaking Bad, the main character gets the nickname Heisenberg. He's talking about this guy right here. So the Heisenberg uncertainty principle. It is impossible to know both the position and the momentum of an electron at the same time. Or another way to say that is, we can't know where an electron is and the speed and direction simultaneously. We can kind of figure out one of those in a moment of time, but we can't know both of them at the same time. So we have to talk in terms of probability. So instead of being like, the electron's here and it's going here, be like, the electron's probably somewhere around here and it's probably kind of going this way. So we had to talk a lot more in terms of probability. So Heisenberg's uncertainty principle sort of led us to that. So I want you to think of this picture of a car. So think about this picture of the car. It's very clear exactly where this car is. Like if we want to measure it, like, okay, this is exactly 3 meters in front of this cone or something like that, which would make this a pretty long car. So it's probably more like 1 meter, but whatever. So we can see exactly where this car is, but can you tell exactly where this car is going? Some of you would be like, oh yeah, well the car is for sure going this way. Like, how do you know that? What if this person, there's a roadblock up ahead and they're actually going in reverse? What if the car is just sitting here parked? From this picture alone, you can tell where the car is, but you can't really tell where it's going. At first, you may think you know where it's going, but you don't actually know. But what about this car? Here we go. This is a picture of a car. So like, okay, where exactly is that car? They're like, well, the brake light is here. Like, there's so much space. Like, where exactly is the brake light? Be like, yeah, I don't know. You can tell me, though, which direction this car's going. It's clearly going this way. There's no arguing that. Like, it's definitely going that way. But where exactly is the car? Yeah. So electrons are the same way as these two pictures. So you either know where it is, but not exactly where it's going, or you might know where it's going, but not exactly where it is necessarily. So we can't know both those things about an electron at the same time, sort of like these pictures of the cars. So the pretty idea of orbits where electrons behave perfectly and they're just going around these nice little circles around the atom, okay, that's just not how things work. It's a nice idea, but it doesn't really explain reality. And so we have this new idea of orbitals. Orbitals. So orbits and orbitals are two different things. Orbits are the perfect little circles. Orbitals are regions of space. They're general areas, regions of space, where there is a high probability of finding an electron. So again, we don't know for sure the electron's in there, but it's like an area where the electron probably is. And each orbital can hold 0, 1, or 2 electrons, but no more than that. So here's what we'll kind of leave things off. On a normal school day, if you were like in your math class or something, and they're like, okay, here's $100, where would you bet Mr. Pilcher is right now? Where would you bet he is right now? Like, well, I can't see Mr. Pilcher, but I would bet that he's probably in his room 245, which I currently am in right now. Okay, do you know for sure I'm there? Be like, no, but I'm speaking in probabilities. He's probably in room 245. That's how it is with electrons. So orbitals are like rooms, okay, where electrons probably are. We don't know they're for sure in there, but they're probably there. They're there most of the time. So my room 245, is sort of like my orbital where I probably am, but you don't know for sure. I might have gone to the lunchroom. I might be making copies. I might have run out to my car. I do all those things during the day. I might have to go to the bathroom, but I'm probably in my room about 90% of the time, and that's what an orbital is. And don't forget, orbitals can hold up to 2 electrons max. This is a max, okay? So it's a 2-seater. You can't get any more than 2 electrons in an orbital. That's an absolute maximum. And that is where we're going to leave things off today. Make sure you take that lecture quiz and get on out of here, nerds. I'll see ya.